Henry has a bacteria, and yeah, he's unfortunately there's 20,000 present in his body right now. Okay, so he's got 20,000 bacteria in his body. And when it gets to 1 million, this thing kills you. Sorry, Henry. I had to sacrifice somebody. Okay, so let's say that that we don't know what the rate of growth is. But what we do know is we counted him again. So this is at noon. He has 20,000 bacterias. Now we counted him again at 1 o'clock. And at 1 o'clock, he had 150,000. Now we've sent off to the main village where they have medicine to have them send the antibiotic back, and hopefully they get back before Henry before his moment comes. So how long do we have? How long do we have to save Henry? All right, well, let's think about this. Exponential growth, and you guys have seen this before. A equals P times E raised to the RT. You probably did. You did this in pre-calculus, and you certainly did it in Calculus 1. Exponential growth. A is the future value. P is the present value or initial amount. E is E. R is the growth rate or decay rate, if we're talking about decay. Because once he dies, then we'll start thinking about the decay of his organic matter. And then T, of course, is time. And then time is going to be according to whatever your units of time you're working with here. We've got hours, right? Because we're going from noon to 1 o'clock, so there's an hour. Okay, well, what's some stuff that I know? I know that at noon, we could call that time 0, couldn't we? So we can say that noon is T equal to 0. Okay, so at 1 o'clock, T is equal to 1. And I could fill some stuff in for this thing, right? So if P is the initial amount, that'd be my 20,000. So I'd have 20,000 here for P. And at noon, my future value is 150,000. And then we have E. Now, what we don't know is the growth rate. We don't know that. But we do know the amount of time that it took to get to 150,000. That was 1 hour. So there we go. Now, what I need to do is solve for R at this point. That's my only variable. So I could divide both sides by 2,000. That's just in the way. 20,000. Thank you. Does that give Henry more time or less time? Yeah, a lot less, right? Yeah. Okay, so good. It's 20,000. So now, let's see. We're going to get some zeros to cancel out, right? So we'll get 4 zeros here to cancel with 4 zeros up there. So that's 7.5, isn't it? So E to the R is 7.5. So now, I got to figure out how to solve for R. What would be the best way for me to do that? Good, yes. So we'll natural log both sides. Natural log E to the R is natural log 7.5. And so R is the natural log of 7.5 because the natural log of E raised to any power is just that power, right? Okay, great. Now I know what R is, and I can go back to this formula that I had, and I can say, okay, I need to know the time when it'll be 1 million. Now, for P, I could use 20,000 or I could use 150,000. I would just have to make sure that I use the right T at the end. But when I solve it, I know which T I'm getting. Now, since we're starting at noon, I think I'll just go ahead and let that be my 20,000 will be my initial value. So let's see. We'd have 1,000,000 equals 20,000 times E raised to the natural log of 7.5 times T. So now, again, we're going to divide both sides by 20,000. And we get a bunch of zeros to cancel out. We get these 4 with those 4. And we have 50, right? We have 50 equals E raised to the T times the natural log of 7.5. I wrote them in the other order to make it easier. Okay, well, it looks to me like I'm going to do a natural log again, right? So I'll go natural log 50 equal to natural log E raised to the T times the natural log of 7.5. And now I can shrink everything. So here we go. We have on the left, I'm going to move this over to the left. We'll have just the T times the natural log of 7.5, right? Natural log of E raised to a power equal to the natural log of 50. So T is going to be the natural log of 50 over the natural log of 7.5. And do we have a time? Did somebody get that figured out? 1.94. 1.94? Ooh, Henry. I hope we have a fast rower going down the river. Now, what time does Henry kick off? Like to the minute. I've got 1:56. At 1:56, we're at 1,000,000. Does everybody get that? 0.94 times 60. Okay, any questions about that? All right, so there's going to be some problems in there that are kind of like that. Okay, now there's another one here. This is the one that I was looking at that I thought was pretty good. So this one says that we have a colony of bacteria is grown under ideal conditions in a laboratory so that the population increases exponentially with time. At the end of 3 hours, there are 30,000 bacteria. Three hours. 30,000 bacteria. And then at the end of 5 hours, there are 50,000 bacteria. How many bacteria were initially present? Now, I can think of a couple of ways we could solve this. But what I do know, no matter what we do, we're involving this A equals P times E raised to the RT, right? No matter what we do. So, what do we know and what can we plug in there? I know that there's 30,000 when T is 3. So maybe I could do this. I could go 30,000 equals P times E raised to the 3R. I could do that. Now I have a similar relationship here. 50,000 when t is 5. And now I actually have two equations and two variables, right? So I could use a substitution property here. Like I could solve them both for p and then set them equal to each other. Like let's do that in the first one. So I'd have, I'd just divide both sides by e to the 3r, right? So in the first one, I'd have p equals 30,000 over e raised to the 3r. And in the second one, I'd have p equals 50,000 over e to the 5r. So now, let's see. Well, if I'm going to solve for p, I can just set them equal to each other, can't I? So I'd have 30,000 over e to the 3r equals 50,000 over e to the 5r. We could cross multiply, or we could, there's lots of things we could do. I think probably what I'll do, though, is I'll just multiply both sides by 1 over 50,000. And also multiply both sides by e to the 3r. And then what that'll do is give me all of the r's on one side, right? And then everything else on the other. So I'll have e to the 3r over e to the 5r equals 30,000 over 50,000. Now, e to the 3r over e to the 5r, I'm dividing with like bases, right? So I would subtract exponents, so wouldn't that leave me with e to the minus 2r? So I'll squish this down. Oh, no, do that. So I'll have e to the minus 2r equals, that's really just 3/5, right? Actually, that also says that e to the 2r is 5/3, doesn't it? Because e to the minus 2r is 1 over e to the 2r. So I'll just make it easier on myself by writing that. Okay, now I want to solve for r, right? So we'll do the natural log on both sides. So we'll have 2r equals the natural log of 5/3. So r is the natural log of 5/3 over 2. Okay, so now I have r. Was that what I was supposed to find? What was I supposed to find? So how could I find p now? I mean, I have two ways, don't I? I have two equations here that I could stick that r in for and get whatever p is. Let's try the one with the 3's. So we'd have 30,000. So p would be equal to 30,000 over e raised to the 3 times natural log 5/3 over 2. Now, when you do that in your calculator, be sure and use your parentheses, right? Anybody get that number? 13943. And then you can check that by putting it in the other one, right? Make sure you get the same thing. So we have, tell me again what you said. You said we could have 50,000 be A.
Yeah.
And then
30,000 be P.
Mm-hmm.
And E to the 2R.
Okay, good. Now, you're going to, and if you do that, you're going to get a solution for R, right? And once you get R, and it'll be the same thing, because if you look at it, you divide both sides by 30,000, you get 5/3. So you got 5/3 equal to e to the 2R, natural log both sides. You got natural log of 5/3 over 2. So that's the other thing you can do. Yeah, you just use the A equals P times E raised to the RT in any way you want, like that. Just use it correctly. Okay? Any questions? All right. So now, so there's some, in section 7.2, and I started with 7.2 on purpose because this is all stuff we know. Like, we're not like introducing anything new here. We're going to go back to section 7.1 and not introduce anything new. Just look at some techniques that we're going to need in order to kind of get our minds going right about using logs in integrals. Okay? So, let's say that, I don't really like that. Well, that problem will be fine. Okay, so let's say that we have something that looks like this. 1 over 14 times the integral of 1 over the square root of x plus x dx. And I'm looking at that and I'm going, I'm going to use a substitution, like, I don't see a function and its derivative there. But I am noticing, though, that I have two terms that have x. And one of the things that we can't help ourselves but do, it's an urge we can't resist. When we're in a situation like this, it's just to factor something, right? So I'm thinking that I'm going to succumb to this urge, and I'm going to factor a square root of x out of the bottom. Now, what did that do for me? Well, let's see. If I was me now and I was thinking about substitution, I'd probably think, you know what? If u was 1 plus the square root of x, then the derivative would put a square root of x on the bottom, wouldn't it? That would be handy. Because that is 1 plus x to the 1/2. So du would be 1/2 x to the minus 1/2 dx, which is 1 over 2 root x dx. And that is really close to what we have there, right? Like if I multiply both sides by 2, I have 2 dx equals 1 over root x dx. And I see that right there. So I'm seeing now a function and its derivative in my integral. Okay, so let's see. Let's do that. So let's do that substitution now. So I'm going to have that 1 over 14 out here. And then I'm going to have an integral. Now let's see. That 1 over square root of x dx is 2 du, right? I misspelled u over here. Is 2 du. So let's see. I'm going to just write that out here, 2 du. And then the 1 plus square root of x part is just 1 over u. So I have 1 over u, and then that 2 du. So I'll multiply the 2 on the outside, and that just becomes 1/7, right? Integral 1 over u du. But that's natural log, right? So I have 1 over 7, natural log, absolute value, right? U, and then plus c. So I have 1 over 7, natural log, absolute value, 1 plus square root of x plus c. But do I need the absolute values? Square root of x is positive, 1 is positive. I'm adding them together, adding two positive numbers together. So I could just write this as 1/7 natural log 1 plus square root of x plus c. Okay, any questions about that? So we're just looking at things that are going to happen that we might not have thought of before. So just like, you see things over and over and over, and you start to get tricks in your mind. So there's a little trick that we might could use. So this is the sort of thing we're going to see in section 7.1. Let's suppose we have... okay. Okay, so the integral of 32 t to the 7th e to the minus t to the 8th. I didn't write that very well, did I? I got too close to the line. To the 8th dt. Okay, so what are you thinking? Maybe t to the 8th, yeah. I mean, that minus t to the 8th looks kind of tempting, but maybe I don't need that. And let's just try it. Let's just see what happens. So we're going to go let u equal t to the 8th. Okay, then du would be 8t to the 7th dx, dt, sorry. So let's see. Yeah, that worked out pretty good, except for that 32 there, right? So I'll just multiply both sides by 4. So I'll have 4 over here and 4 over here. And I'll have 4 du equal to 32 t to the 7th dt, which I have. So I've got e to the minus u times 4 du, right? And then I'll just put the 4 out front. So I'll have 4 times the integral e to the minus u du. But what's the integral of e to the minus u? What's that? No, you might have been right.
I don't think I was. I was doing the derivative instead of the antiderivative.
Well, are they different?
You have to put 1 over e to u and then become natural log of
No, but I could put that 1 over e to the u. I could do that, but do I have to do that?
No, because the derivative of e is the same thing as...
Yeah, e to the u, the derivative of e to the u is e to the u, right? it is its own integral and its own derivative.
So it's just negative.
Yeah, you were right.
Oh, I was.
So it's just minus 4 e to the minus u plus c, right? But let's see, what was u? U was t to the 8th. So we have minus 4 e to the minus t to the 8th plus c. Okay? Okay, and then we might have limits of integration on these things. So let's suppose we have the integral of let's see, we're going from the natural log of 3 pi over 2, ooh, that looks good, up to the natural log of 11 pi over 6. Sounds to me like maybe some, yes. Some trig functions are coming. Those are V's. What are you thinking you ought to be?
E to the v.
Probably, I'm thinking that because the derivative, because the integral of cosine is just sine, right? So if I can get something looking good that way, so let's give it a try. So we're going to let u equal to e to the v. Then the nice thing, of course, is that du would just be e to the v dv. And we got that. Except we got a 2. So I could multiply both sides by 2. And I'd have 2 du equal to 2 e to the v dv. Now, I have a choice here. In the end, I'm going to either need to substitute those limits of integration after substituting back, or I could substitute them now, right? Like I could find the limits of integration in terms of u. And I'm looking at what u is, and it's e raised to a power, and I got natural logs there. I'm thinking I'm going that route. So let's see. Let's find u of the natural log of 11 pi over 6 and u of the natural log of 3 pi over 2. So in other words, what's the value of u when v has those values? So let's see. Well, we've let u be e to the v, right? So this will be e raised to the natural log of 11 pi over 6. And, well, e raised to the natural log of an argument is just the argument, right? So just 11 pi over 6. That's nice. And then this will be e raised to the natural log of 3 pi over 2, which will just be 3 pi over 2. And this is working out nice since we've got a cosine function going here. Okay, so let's see. Now, we're going to make all these substitutions. So now I'm just going from 3 pi over 2 up to 11 pi over 6. Now, 2 e to the v dv is 2 du, right? And then u is e to the v, so I just have cosine u here. Okay, so let's see. We've got 2, and then we've got sine, right? Sine u evaluated from 3 pi over 2 to 11 pi over 6. So we have 2 sine 11 pi over 6 minus sine 3 pi over 2. Now, so this is where your trig comes in handy, right? Where you need to kind of remember that stuff. So let's think about 11 pi over 6. on the unit circle here. And so 11 pi over 6. Isn't that just 1 pi over 6 shy of 12 pi over 6? So almost 2 pi. Actually, an angle with the reference angle of pi over 6 in the fourth quadrant. Okay, so now let's think about a triangle that has a reference angle of pi over 6, a right triangle, pi over 6. The sides of that are 1, 2, and square root of 3, right? So the sine of pi over 6 is a half, but we're in the fourth quadrant. So what is that going to be? Yeah, negative a half. Very good. So we have 2 times negative 1/2 minus. Okay, now 3 pi over 2. Well, 3 pi over 2 is just this one that's straight up and down, right? Down here on the bottom. And what's the sign there? Yeah, negative 1. So we have minus a half plus 1. That's a half times 2. Well, that's just 1. And what's the crazy thing about that? If you graph that, 2e to the v cosine e to the v, between 3 pi over 2 and 11 pi over 6, what are you going to find?
Its area is going to be 1.
Yeah, that's how much paint you need, right? 1 can. Yeah, that's crazy to me. Like that it's 1. It's not like, something e with a pi in it and everything else. Okay. Any questions about that? This is pretty accessible, isn't it? Okay. I'm going to let you guys work on one. Let's have you do this. So, integral dx over 5x log base 7 of x. Let me talk about that one for a second, though. But like when you see log base 7, what's the first thing you think? I got that on my calculator. That's what I think. What do I have on my calculator?
Not sure.
I don't really need it on my calculator, right? But if I was to ever have to do, a convenient estimation of the value, which we're not going to do, but if I had to, you'd either want log 10 or log natural log, right? So what are you thinking you probably might do with that log base 7? Maybe do a change of base and make it natural log? That's what I think I'm doing, also because the integral formulas they're a lot nicer with the natural log than they are with logs of other bases. So I'm thinking the first thing I'm going to do is do a change of base on that. Make it natural log. So it'll be natural log x over natural log 7, right? In case you don't remember that. So did you get it to that form? Because for me now, I'm looking at that natural log x, and I'm saying, okay, if I was to let u be the natural log of x, then du would be 1 over x dx, right? So, yeah, that's pretty nice now. Because now what I've got is natural log 7 over 5 integral 1 over u du. So, integral 1 over u is natural log u. So I've got natural log 7 over 5, natural log absolute value of u plus c. And then, well, u is just natural log x. So what we have is natural log 7 over 5, natural log of x plus c. Initial value problems. Okay, so they're going to look something like this. Okay, so I know something. I know that that dy dx is equal to 9 plus 1 over x. So I know that. And then I also know that y of 1 is 11. So here I've got the derivative, 9 plus 1 over x. And then I know that the value of the function y, so like before I took a derivative, when x is 1 is 11. Okay, so, well, what do I need to do then? Well, what I probably need to do is say, well, okay, so let's express this as dy equals 9 plus 1 over x dx. We might do that. And then we might say, okay, you know, I might do a substitution now. So I might let u be x, which doesn't seem to do anything at all, does it? So maybe I just power through it the way it is. So I go, okay, what if I was to find the integral, then, of 9 plus 1 over x dx? I think I can do that. What's that going to be?
9x plus natural log x plus c.
Plus c. And so that right there, and it's the absolute value of x, right? That's the interesting part there. Okay, so now y is equal to this, right? So y is equal to 9x plus the natural log of the absolute value of x plus c. Okay, but what I know is that if x is 1, then y is 11. So I could substitute all that right here. I could say, okay, 11 is equal to 9 times 1 plus the natural log of 1 plus c. And the natural log of 1 is 0, right? And 9 times 1 is 9. So what I have here is 11 equals 9 plus 0 plus c. Okay, so now if I subtract 9 from both sides, I have c equal to 2. And so now what I've done here is I have solved this initial value problem. So I have an initial value, that y of 1 is 11, and I have a derivative. So to find this function then, y, it would be 9x plus natural log absolute value of x plus 2. You guys I know you're vaguely aware of what hyperbolic functions are. You had to have seen them in some pre-calculus class at some point. But they look like this, the hyperbolic sine of x. And what they are exponential functions, and that's why we're looking at them right now, is because it goes along with what we were looking at. So the hyperbolic sine of x is e to the x minus e to the minus x over 2. And then the hyperbolic cosine of x is e to the x plus e to the minus x over 2. Now the reason that they have these trig names is because they behave very similarly to the trig functions with regard to identities, not exactly the same, but similarly. With regard to identities, derivatives, and integrals. Okay, now, without actually going through the process of graphing these things, I'll just put a couple of them up here, what they look like. So right here is the hyperbolic sine. Hyperbolic cosine looks like this. Kind of like a fat parabola. Hyperbolic tangent looks like this. And then, whoops, that's not at all what it looks like. There. And then it's not really important right now that we look at what the other graphs look like, but just kind of a basic awareness of what these graphs look like. And you can kind of imagine, like the hyperbolic cosine, look at the numerator terms. You got e to the x and e to the minus x. Those are both positive, right? And then I'm going to divide that by 2. So I know I'm going to take e to the x and then add some value to it. So now I'm over 2, close to 3, right? And then I'm going to divide that by 2. So the smallest I'm really going to be is, what, like right around 1. Okay, and then the hyperbolic sign, well, I'm subtracting. So when I get down to really big negative numbers, my e to the minus x is going to overtake my e to the x, right? And I'm going to wind up with negative values. So that's why we are negative then to the left of the y-axis for hyperbolic sine. Yes, sir?
Is the hyperbolic tan just hyperbolic sine over hyperbolic?
Yes, it is.
Okay, so that.
Yeah. So there are, we're going to look at a bunch of that kind of thing. Now, let's do this. Let's look at, well, I tell you what, let's do. Let's find the derivative of the hyperbolic sine. Let's do that. So if y is equal to hyperbolic sine of x, that means that it's equal to e to the x minus e to the minus x over 2. So let's find the derivative of that. So dy dx then is going to be, now let's see, I could call that e to the x over 2 minus e to the minus x over 2, right? I'm sorry, y. I could call y that. I didn't mean to say dy dx yet. And it would be easy to differentiate from that point, right? So dy dx, let's see. Well, I mean, that's just going to be e to the x over 2, right? And then what's that going to be? That's going to be plus e to the x over 2. Oh, minus x over 2, rather. And then that is e to the x plus e to the minus x over 2, which is,
Cosine.
yes, hyperbolic cosine. So you see then that there's one of the reasons why these things are called, have their trig function names, because they're going to behave very similarly to that. Now, so let me ask you this. What do you think the derivative of the hyperbolic cosine is?
Negative hyperbolic sine.
No, positive. So it's positive hyperbolic sine, but I was hoping you'd say that. So you see then that they're not going to behave exactly the same. There's going to be variation, and we're going to have to know what those variations are. And I tell you what, let's make ourselves a little table. So let's make a table of the functions themselves and then their derivatives. So the function hyperbolic sine, its derivative is hyperbolic cosine. The function hyperbolic cosine, its derivative is hyperbolic sine. The derivative of hyperbolic tangent is, what do you think? Yes, hyperbolic secant square. derivative of cotangent is minus hyperbolic cosecant square. Hyperbolic secant derivative minus hyperbolic secant hyperbolic tangent, and derivative of hyperbolic cosecant is minus hyperbolic cosecant hyperbolic cotangent.
Will we be learning the antiderivative as well?
Oh, good idea. So the integral of hyperbolic sine is, oh wait, I should have put a dx there, shouldn't I? Is hyperbolic cosine plus c. The integral of hyperbolic cosine is hyperbolic sine. And none of this now, plus c, is very, and that's not surprising because we've got these derivatives sitting right here in front of us. So, but they're not all going to behave nicely because the derivatives aren't nice the whole time, right? So let's see. The hyperbolic secant square. Oh, shoot. I always forget to put the h there. Is going to be the hyperbolic tangent. And on and on and on down like this. Now, so where it's going to get different is when we get to like integral of hyperbolic tangent, integral of hyperbolic secant, things that we don't see here in the table. Like it was easy for me to put hyperbolic secant square because that appears in the derivative side of the table, right? But for the ones that aren't that nice, I don't memorize that stuff at all. Like I couldn't have sat down right here and told you. Well, I could have, but for like hyperbolic tangent and all that other kind of stuff, I look that up every time. I never memorize that stuff. Okay, so here's what I would like for you to do, please. I would like for you, please, to find, so let's do this. Let's say y is equal to hyperbolic sine of x squared. So please find y prime. What rule are you thinking you're in for here? Yeah, I think chain rule. Yeah, good. Because you got a function in a function, right? So, I'm thinking, my outside function is hyperbolic sine, right? So I'm going to do the derivative of the outside times the derivative of the inside, right? So the derivative of hyperbolic sine is hyperbolic cosine. And then the derivative of x squared is 2x. So it's just nothing more than that. But I know what you're thinking. You're thinking, boy, don't know. He keeps saying something about the hyperbolic tangent, but he didn't tell us what the derivative of the hyperbolic tangent is. Or did I? Yeah. But but I didn't tell you what the integral of the hyperbolic tangent is, did I? So maybe you want to find that. What do you think? What did you ask me a little bit ago?
I was gonna do sine of x over cosine.
I think that'll probably work. Because you asked me a little bit ago, well, is the hyperbolic tangent same as hyperbolic sine over hyperbolic cosine? And I said, yeah, it is. So why don't you give that a whack and see if that gets you somewhere. So is that what you guys got? Natural log of absolute value of hyperbolic cosine plus c. I'm wondering if we need those absolute values. What did we decide about the hyperbolic cosine a little bit ago? It's always positive, yeah. And is it ever less than, is it ever less than 1? No, it's not. Even. So yeah, we don't even need the absolute values there. When we're working with real numbers. Okay, so now, you're also thinking, boy, I sure am curious about those inverse hyperbolic functions. Like, say, for instance, the inverse hyperbolic sine. Well, I tell you, before we can worry about calculus on inverse hyperbolic functions, there's some things that we're going to have to get clear on. Because what is it about the hyperbolic, or what is it about the inverse trig functions that allows you to even do the calculus stuff? Or that even allows them to even have inverses? What's the thing?
They have a restricted domain. Sorry, go ahead.
Yeah. Why is that? Because the functions have to be, yeah, they have to be 1-to-1, right? Okay, so we got to make sure then that we're dealing with 1-to-1 functions when we're looking at the hyperbolic trig functions. Okay, so if this is our function, a hyperbolic sine, then where would that be defined? Well, the domain would be all real numbers. And the range would be all real numbers. Looking at that graph, is that a one-to-one function with a domain of all real numbers and a range of all real numbers? Yeah, it is. Okay, good. So that's not surprising. Okay, what about hyperbolic cosine? Now, the domain is going to go from 1 to infinity, and the range is going to be from 0 to infinity. Wonder why that is. So let's look at that hyperbolic cosine for a second. So hyperbolic cosine of x is e to the x plus e to the minus x over 2, right? Okay, so let's see.
That's the regular, or is that the?
I mean, that's the regular. I didn't mean to say hyperbolic. Sorry, I mean the inverse. The regular hyperbolic cosine. Okay, so now let's see. So can I put, like, if I was to put 0 in for x here? So the hyperbolic cosine of 0 would be e to the 0 plus e to the minus 0 over 2. Well, that's just 1 plus 1 over 2. That's 1, right? Let's put something other than 0 in there. Let's put 1 in there. Okay, so I'd have e to the 1 plus e to the negative 1 over 2. Okay, so that would be e plus 1 over e over 2. Okay, well, that's bigger than 1, right? Because I'm taking a number that's bigger than 2, e, adding a value to it, and I'm getting something that's bigger than 1. Okay, so I know I'm going up, right? Now let's do hyperbolic cosine of negative 1. So what if I go the other way on the along the x-axis? Okay, so let's see. I'd have hyperbolic cosine of negative 1. Okay, so that's going to be e to the minus 1 plus e to the positive 1 over 2. It's the same thing, isn't it? Okay, so that is now explaining why this graph has this shape on either side of the y-axis. Now, is that one-to-one? No, it's not. And if I want it to be one-to-one, I'm going to have to get rid of part of it, right? I'll have to restrict the domain. So I would restrict the domain from 0 to infinity. But this over here says the domain is 1 to infinity. And the range is 0 to infinity. Why is that?
Because you swap them.
That's right, because to get an inverse, you just swap the x's and the y's. So just making sure that we have a complete understanding of how these things are working here. Okay, all right. All right, so let's look at the inverse hyperbolic tangent. So that is going to have a domain of minus 1 to 1 and a range of negative infinity to infinity. Now, all these things are, I mean, the reason for all these things are going to be similar. We'll just look at the graphs or look at the functions themselves and determine what they're doing. So I'm not going to go over all of them, analyze them like we did on the last one. So inverse cotangent has a domain that starts at negative infinity, then goes to negative 1, and then it skips some and starts back up at 1 and goes to infinity. And then its range is going to be minus infinity to 0, and then it's just going to skip 0. That's all it's going to skip. And the reason for that is because the hyperbolic cotangent, which I didn't put that down, but that particular graph has a kind of a rational function graph. You know how they would have something that would look like this? Like your rational functions. Remember when you graphed 1 over x and it looked like this? And it had an asymptote like that? Well, the hyperbolic tangent is similar to that, except there's a big gap. You wind up with a big gap in the middle. And then that's what's going to happen. That's what's going to cause it to have that particular domain and range. Okay? Let's see. Hyperbolic secant is going to go from 0 to 1 domain, and then 0 to infinity for range. And you can kind of imagine about cosine and secant, right? They are inverses of each other for trig functions. And then hyperbolic cosecant, minus infinity to 0, union 0 to infinity. And then same thing, minus infinity to 0, union 0 to infinity. Okay, so when we're working with the hyperbolic inverses, those are some of the things that we sort of have to keep in mind, and we could look at those graphs if we wanted to. How much time we got? Okay, so I'm running out of time, but I wanted to look at what some of the derivatives. This section is not difficult. It's all you're doing is just algebra with those exponential functions, e to the x and e to the minus x, which you've done that lots of times. It's just that we're doing them sort of in the context of these hyperbolic functions now. So let's do this. Let's take a function y equals hyperbolic inverse of x. And let's find the derivative, okay? Now, if y is the hyperbolic inverse sine of x, then what's x? It would be, wouldn't it? Because that's what an inverse function is, right? So in other words, I could write this. Now, what I'm going to find, though, is I'm going to find dy dx, right? I want the derivative of the hyperbolic inverse hyperbolic sine function, right? So I'm going to be looking for dy dx. Now, if I do a differential on this, what I've got on this line right here, hyperbolic sine of y equals x, what would I have to do on the left? Do you remember the technique that you did in Calculus 1?
I know what it's called.
What's it called?
Implicit differentiation.
Yeah, you're going to have to do an implicit differentiation, right? Because y is a function of x. Y is a function of x. So you have a chain rule here, don't you? You've got an outside function, hyperbolic sine, and an inside function, y as a function of x. So what is that derivative going to look like then? Well, outside function, that's going to be hyperbolic cosine, right? Hyperbolic cosine of what? Of y, right? But then you've got to multiply that by the derivative of the inside function, which is going to be dy dx. Now, the derivative, and what we're doing here, of course, the derivative of the right side is just 1, right? To do an implicit differentiation. Okay, now, I want dy dx. So couldn't I just divide both sides by hyperbolic cosine y? Okay, so dy dx would be 1 over hyperbolic cosine y, but what is the problem with that? Man, what's your problem?
It's in terms of y.
It is in terms of y. So what's your plan? What are you thinking?
Substitute y for sine or hyperbolic sine or inverse hyperbolic sine of x, or
Yeah, I don't know about that. We might need an identity. Maybe we should refer to an identity. And this, of course, the purpose here was to introduce how some of the identities work in for hyperbolic functions. Okay, so here we go. What's the first identity that you would really want to know? Like when you do trig identities, what's like the most important one that you just use over and over and over and over and over? The Pythagorean? Sine squared plus cosine squared is 1? Yeah. So how does that work with hyperbolic functions? Okay. So, oh, darn it. It works like this. Square of hyperbolic cosine minus square of hyperbolic sine is 1. So if I was to add square of hyperbolic sine to both sides, I'd have square of hyperbolic cosine equal to 1 plus square of hyperbolic sine, right? Darn it. I'm getting in a hurry and I'm making it messy. And if I was to square root both sides, do you see how it's starting to get kind of handy now? Why am I not doing plus or minus on the right over here? What do I know about hyperbolic cosine? It's what? Yeah, it's always positive. Okay, now. Wait a second. Look, I got hyperbolic sine square of y. What's that? Is that x squared? Look up here. Hyperbolic sine of y is x. So the square of that is x squared, right? So wouldn't hyperbolic sine of y then be equal to the square root of 1 plus x squared? And then doesn't that mean that this derivative would be equal to 1 over the square root of 1 plus x squared?